So I thought it'd help if I put together some related rate problem examples for you to take a look at this weekend, so I don't hit you with it all at once when we come back on Tuesday. The couple of examples I'm going to do are coming from this website right here. So you can go and take a look at that. They have several types of examples on there, and I'm going to do 2 of them. So take a look at that. That'll give you an idea of all the different types of applications we can do with this. So let's go ahead and take a look at the first example. The ladder problem is one similar to what we did in class, but I thought it might be useful for you to see it again. So we've got a 15-foot ladder is resting against a wall. So the ladder is 15 feet. The bottom is initially 10 feet away from the wall and is being pushed toward the wall at a rate of 1/4 foot per second. How fast is the top of the ladder moving up the wall 12 seconds after we start pushing? Okay, so we've got several things happening. We've got all of our basic information. Okay, first of all, let's go ahead and call that x. Let's call that y. Okay, we all know that x squared plus y squared is equal to 15 squared, right? Okay, that's going to be the basis of our relationship. Okay, we've got a relationship now between the length or the distance on the ground and the height on the wall. We also know that dx dt, how fast is x changing with respect to time, is equal to -1/4. Why is it negative? What's the distance doing if you're pushing the ladder toward the wall? X is getting smaller. If x is getting smaller, its derivative has to be negative. Okay? We also have a snapshot right here, 12 seconds after we start pushing. Now that's going to be we have a little twist to that, but we'll get to that in a minute. Let's go ahead and find the relationship here between the rates. Okay, we're trying to find a derivative, or how fast things change with respect to time, with respect to seconds. So that's going to tell us how we're taking our derivative. We're going to take our derivative with respect to time, and so we end up with this equation. Let me erase that and do that again. 2x dx dt plus 2y dy dt equals 0. Okay, that's our basic relationship, and I can get rid of the 2's. So we can have x dx dt plus y dy dt equals 0. Okay, here's our equation that relates our rates. Get it? Related rate problems. Okay, now our snapshot is 12 seconds after we start pushing. We don't have time anywhere listed here. Okay, but we do have x and y. Okay, so what we've got to do is figure out what we need to plug in for these quantities. Okay, we know dx dt is -1/4, so that's easy. If we're pushing for 12 seconds at 1/4 foot per second, how far have we pushed? 1/4 foot per second times 12 seconds is equal to 3 feet. If we started at 10, we now know x has to be 7. So x is equal to 7. dx dt we already figured out was -1/4. Now we just have to figure out y. Well, if we know this is 7 and that's 15, then we can figure out, using a Pythagorean theorem, what y is. We know that 225 minus 49 and the square root of that, that's what y has to be equal at that snapshot. So if I do that on the calculator real quick, I get 13.266. 13.266. So y is equal to 13.266. Got everything we need. Let's plug it all in. 7 times -1/4 plus 13.266 dy dt equals 0. Why didn't I find anything for dy dt? Because that's what I'm trying to find. How fast is the top of the ladder moving up the wall? So basically, how fast is y changing? And that's what we needed to find out. So now we can just simplify this. Dy dt equals -7 or +7/4 over 13.266, and if I divide that out, I get 0.1319 feet per second. And that's how you do that problem. Pretty cool, huh? Important thing to remember when you're doing these problems is be careful of the signs. Be careful of the pluses and the minuses. You've got to make sure that your derivative value agrees with the direction of travel of the quantity it's the derivative of. Okay? If we had put positive here instead, what that would have meant was the ladder was being pulled away from the wall because x was getting larger, and that wouldn't have been correct. We would have ended up probably with the same number, but it would have been negative instead because y would have been shrinking instead. Guess I got to answer the phone now. So there's example 1. It was a junk phone call. All right, let's go to the next example. This is going to be a little bit different now. Okay? So two people are 50 feet apart. One of them starts walking north at a rate, so the angle shown in the diagram below, where's the diagram below? Let me go grab that. Like magic, isn't it? So the guy started right here, and then he started walking north. And he's walking north at a constant rate of 0.001 radians per minute. That's how fast this angle is changing. It is increasing by 0.01 radians per minute. So the question is, at what rate is the distance between the two people changing? So that's this distance right here. Okay? Well, this is another type of relationship that you'll find common in related rate problems. This is a trig relationship. Notice you've got 50, you've got the hypotenuse, and you've got an angle. So, pretty easy to figure out here that cosine of theta is equal to 50 over x, right? Adjacent over hypotenuse. There's your relationship. You got a relationship between theta, the angle, and x, the distance. So, we can find the derivative. Okay, let me just rewrite that as 50x to the negative 1. That'll help us with our derivative. The derivative of cosine theta with respect to t, because we're finding how fast the distance is changing. Okay, with respect to t is going to be negative sine theta d theta dt. Right? Composite function. Outside, inside, because theta is a function of t. Theta depends on what the time is. Equals, this is negative 50x to the negative 2 times the derivative of x with respect to t. Same idea. Outside function, inside function. Okay? Now, let's go ahead and plug in what we know. d theta dt is equal to 0.01. Is it positive or negative? Right, it's positive because theta is increasing as this guy moves forward, or moves up. dx dt we're trying to find, okay? And theta, we need to plug that in. Where's the snapshot? Snapshot's right here at 0.5 radians. So let's plug in what we know. Negative sine of theta, d theta dt is 0.5, or 0.01 I mean. So 0.01 equals negative 50 over x squared dx dt. Okay, the last problem we have is we've got to figure out what theta is, and we've got to figure out what x is at the snapshot. Okay, so that's pretty easy to do. Let's just put that off to the side here, and I'll put that in red. When theta is equal to 0.5, then I know the cosine of 0.5 has to be equal to 50 over x, right? Well, now we can figure out what x is. I'll get my calculator and figure that out. So I figured out x was equal to 56.9747. So we can plug everything in now. Negative sine of 0.5, because that's our snapshot, times 0.01 equals negative 50 over 56.9747 squared times dx dt. Okay? So now you figure all that out, figure out what dx dt is, and that's just some algebra, which you can do. Dx dt ends up being 0.3113. That's if you compute all this stuff out. Okay, I'm almost to my 10-minute limit. Look at that. Time to stop.